Welcome to Petrochronics, a research group and extension project focused on petrochronology and its geodynamic implications.
We are a group based in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTt-talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
Hello, everyone. We stay alive in another PTt-talk. I'm so glad to be here today with our speaker, Veronica Peverelli. Bruno, Regiane, Guto, and Maíra will be hosting the talk with me. We are Petrochronics, our research group from Brazil, and this talk is one of our initiatives. So we here again. Thank you, Veronica, for accepting this invitation. And at the end of the talk, we will have some time available to do and answer some questions. Maíra, it's with you. Maíra, your phone.
Thank you, Veronica, for joining us today for the talk. It's a great pleasure to have you. And I will just give a brief summary of Petrochronics. So we are a Brazil-based research and extension group. And we also have an expanded network of international collaborators. And we are focused on the scientific communication of petrochronology and its geodynamic implications, promoting geological discussions among peers working in related fields, and the insertion of newly interested students and geologists. And as you could see in the video, our actions include organization, promotion, and hosting of open and free lectures, as this one, and courses, workshops, and meetings. And We are very happy to have this community, and if you want to know more about it, you can have a look on our website. So now it's with you, Regine.
Thank you. Good morning, or afternoon, or evening. First of all, I'd like to thank Veronica for accepting the invitation to give the talk here and the people that are watching the PTt-talk now. This is our PTt-talk number 17. The PTt-talk series is one of the Petrochronics group actions, which are presentations on methodologies and advances in cutting-edge research with petrochronology. The previous PTT talks are recorded here in our YouTube channel, so we invited those who haven't watched them yet to visit our channel. Thank you very much, and I will leave with you good now.
Hello, everyone. And first and foremost, thanks, Veronica, for joining us. I'll give a brief presentation of Veronica's previous work. She graduated in geology at the University of Milan, initially investigating halogens in the lithospheric mantle, and her work was focused on the Canary Islands. Then she moved to her master's degree in the same institution, but in this case, studying the concentration of halogens in peridotic xenolites from continental and oceanic lithosphere. Moving to the University of Bern for her PhD studies, there she developed a project on Epidote uranium-led geochronology and isotope geochemistry as a tool to trace hydration of continental crust in orogens, defending her thesis earlier this year. She soon to assume a new position at the University of Bologna in Italy, working on an IRC-funded project. Bruno will give a brief introduction of the talk now.
Thank you. First, I want to welcome Veronica to our talk, well, to her talk mostly. And as a geochronologist myself, I'm really curious about this talk, because one of the most difficult things is studying fluid percolation through the crust. And today, Veronica will talk about how we can do this, dating epidote and deformed granites through the continental crust. Really well, doing in situ laser ablation, which is pretty cool. So having a nice textural control. I'm very curious to see how these go. I just saw your new geology paper. Congratulations. And I think you can start it off.
Very good. So thank you very much for the introduction and for the invitation, of course, to present today. Sorry, I'm going to go back and start my presentation. There we go. So today I will talk about Epidote uranium-led geochronology and Epidote isotope geochemistry, and I will show you how we can use Epidote to date and trace fluid circulation in the continental crust in the alpine orogen. And although today I will specifically talk about the alpine orogen, much of what I will say can actually be applied to the continental crust in other orogens. To discuss the evolution of the continental crust in the alpine orogen, we have to keep in mind that what we see today is actually the result of a really long geological history that we may start discussing from Permo-Carboniferous times, when we had continental rifting under a transtensional regime. After that, we had a pretty famous phase, the Jurassic rifting phase, that led to the breakup of Pangaea and to the opening of the Tethys Ocean with the formation of passive continental margins on both sides of the Tethys. In late Cretaceous times, we had tectonic inversion with the subduction of the European plate under the Adriatic plate, and this led to the closure of the Tethys Ocean. And finally, about 35 million years ago, we had a continent-continent collision and the alpine orogeny. So during the tectono-metamorphic evolution of the continental crust during orogeny, fluids play a fundamental role. Fluids are involved in both prograde and retrograde metamorphic reactions, but they also control deformation processes. And the primary water contents of the lithologies that mainly constitute the continental crust are actually quite low. However, we have the possibility of adding water to these rocks throughout its evolution. So here, during continental rifting, we may have surface water percolating into the continental crust, exploiting may have some pretty complex hydrothermal systems. And the point is that any sort of rock alteration that takes place before the involvement of the continental crust in orogeny plays a role in preconditioning the continental crust for deformation during orogeny. And a notable example is the fluid-driven alteration of feldspars. By feldspars, just to be clear, I mean plagioclase and K-feldspar. And the reason why feldspars are so important is that they dominate granitic rocks, and granitoids dominate the continental crust. So if you want to address the deformation of the continental crust, we have to talk about granitoids, and we have to remember feldspars. So a fresh, unaltered granitoid is a pretty strong rock that will not deform very easily. But if we add water to this rock and we alter feldspar grains into hydrous alteration minerals such as epidote and cerussite, which are the highly birefringent minerals in these feldspar grains, then the altered granitoid is more easily deformed into a mylonite. And this is related to the fact that fluid-driven alteration of feldspars leads to the storage of water in the form of hydrous alteration minerals. It increases the abundance of weak minerals such as sheet silicates, and it also causes the grain size reduction of coarse feldspar grains. And the interplay of this leads to the overall weakening of the granitic continental crust. If this happens before the onset of orogenic processes, then the related deformation processes are facilitated. Unfortunately, evidence for pre-orogenic fluid circulation in the continental crust is actually very scarce. And to be honest, in the study areas, it was basically and so this let us wonder if any pre-orogenic fluid circulation actually occurred in the study areas. And because of the long geological history of the continental crust in the Alps, we believed that pre-orogenic fluid circulation did occur. And today, uranium-led geochronology of Epidote will demonstrate exactly that. So, how do we date ancient fluid circulation if, of course, the fluids are no longer there? So we have to date the direct evidence for fluid circulation, such as the filling of a fracture by a mineralizing fluid, leading to the formation of a vein. So if we date the vein filling minerals, then we know when fluid circulation occurred. And ideally, we would like to target minerals that are common and that are not easily affected by post-crystallization processes. And good candidates for this are minerals of the Epidote clinozoisite solid solution. Here you have a really nice example. And I will simply call, minerals of the Epidote clinozoisite solid solution is a long phrase, so I will simply call it Epidote for the rest of the talk. So Epidote is a common vein filling mineral, and here you have two examples. So this is an Epidote vein from in a plagiogranite from Troodos in Cyprus. And these yellowish bands are Epidote veins in a deformed tonalite from the Iberian margin. Epidote has a wide stability field from lower green schist species conditions to amphibolite conditions. It is also stable at high pressure, and it is actually not shown here, but Epidote is stable also at high temperature. Epidote has high closure temperatures for diffusion. Fluid tracer. So a geochronometer is a pretty straightforward concept. We want to know how long ago it formed. And what is a fluid tracer? So I will introduce it using a pretty famous beverage, which is coffee. So when you make coffee using a coffee percolator, you add water here, you add ground coffee there, you heat the water, so the hot water percolates through the coffee, interacting with the coffee, and finally you have your cup of coffee. So when you drink your coffee, you will be able to tell if the water you used was tap water or seawater. Because the moment you take a sip of coffee, if you used seawater, it will be absolutely disgusting. At the same time, coffee lovers may be able to tell if the coffee that you used was Robusta or Arabica or a mixture of both. So the point is that there are features in your cup of coffee that will tell you about the water that you used, and there are features in the cup of coffee that will tell you about the coffee with which the water interacted to make your coffee. So back to our epidote veins. The isotope ratios of some elements will tell you about the fluid sources, and the isotope ratios of some other elements will tell you about the rocks with which the epidote forming fluids interacted. So now I've given you an overview of why we do what we do, and the rest of the talk is subdivided into three parts. First, I will introduce epidote as a uranium-lead geochronometer. And then we will apply the protocol to epidote veins from two inverted passive continental margins in the Alps. So I should remind you that our goal is to date and trace fluid circulation in the granitic continental crust in the Alpine orogen. And we do so by studying or by using epidote in hydrothermal veins in deformed granitoids from two inverted passive continental margins. So let's talk about epidote dating. So to calculate the age of a mineral that contains a radioactive element, you need to know the equation for radioactive decay, and you need to know how long it takes for half the initial amount of the parent element, which for us is uranium, to decay into its daughter element, which for us is lead. This is called the half-life. And the equation allows us to calculate how long has passed since the isotopic system was closed or frozen, if you wish, inside our geochronometer. So epidote does contain fair amounts of uranium. Unfortunately, it also contains large amounts of lead. And lead in epidote is actually dominated by the fraction of lead that epidote incorporates during crystallization from the epidote forming fluid, and this is called the initial lead. And it's a problem because for age calculation, we don't use initial lead, we use radiogenic lead. So the lead that is produced inside the mineral by the radioactive decay of uranium. And ideally, we would like to remove the contribution of initial lead from total lead in order to obtain radiogenic lead and calculate the age. This can only be done, however, if the isotopic composition of initial lead is known, can be measured, or can be reasonably assumed. And for hydrothermal epidote, this is seldom, or I should say never, the case. And wrong corrections for initial lead lead to grossly inaccurate ages. However, minerals of the epidote supergroup, such as allanite, have been successfully dated. And what these works have in common is that they found the right protocol. So that's exactly what we have to do. We have to find the right protocol for our purpose. And luckily for us, to date high initial lead minerals, we can use the Terra-Wasserburg diagram, which is shown here. And it plots lead-207 to lead-206 versus uranium-238 to lead-206 ratios that are not corrected for initial lead. So our regression, which is the blue line, is fit through a number of single analyses, which are the blue ellipses. And the intercept between this regression and the y-axis gives you the initial lead-207 to lead-206 ratio. This is the isotopic composition of lead that epidote incorporates from the epidote forming fluid. So we can use it to investigate fluid pathways. So back to our coffee pot, we can investigate the rocks with which the epidote forming fluid interacted. And the h is given by the lower intercept between the regression and the Concordia curve, which is this blue curve here. So h uncertainty is determined by how well constrained the lower intercept is, and this is controlled by the spread of the single analysis along the regression. This is controlled by the variability in total uranium to lead elemental ratios. And how do we ensure that we have the largest variability possible in uranium to lead ratios? We do so by making sure that we sample every possible chemical domain inside our epidote sample. This is a chemical map, so the black is quartz and everything else is epidote. And basically you see the variability, so the spatial variability in iron to aluminum ratios. This sample doesn't contain chromium, just for you to know. So what you see, this is actually by microprobe also. What you see here is that the variability in major elements, which are iron and aluminum, is quite high in this epidote sample. And variability in major elements can reflect variability in trace elements, such as uranium and lead. So ideally, to date epidote, we would like to use an in situ technique that samples small volumes, such as laser ablation inductively coupled plasma mass spectrometry, or LAICPMS. And here we have our second problem, because LAICPMS requires the use of a standard, and ideally we want the standard to have the same matrix as the sample. The reason for this is that during ablation, so as we drill down in our sample, uranium and lead are fractionated from each other, and the pattern of this downhole fractionation depends on the matrix that we are ablating. So for epidote dating, we would like to use an epidote standard, which does not exist. However, we may try using allanite as a reference material, because allanite is the rarest element-rich member of the epidote supergroup. So we may assume that the matrix of allanite is quite similar to that of minerals of the epidote clinozoidite solid solution that we call epidote. And there exist well-characterized allanite reference materials. But we actually have to prove that epidote and allanite are sufficiently matrix matched. And we did so by plotting the lead-206 to uranium-238 ratios of single analysis. So each color is one analysis during ablation, which begins here and ends there, corrected for downhole fractionation using allanite as a reference material. So the concept is that if the patterns are flat and they overlap, then the correction for downhole fractionation is accurately carried out. And this is the case for epidote using allanite as a reference material. This entails that epidote and allanite are sufficiently matrix matched, meaning that we will calculate accurate ages from accurate isotope ratios. Of course, we wanted to double check the calibration of our protocol, excuse me, and we did so by plotting the same isotope ratios measured by an independent technique, which for us is solution ICP-MS. And we plotted them in a Tera-Wasserburg diagram along with LA-ICP-MS data points. So LA-ICP-MS data points are the blue ellipses, and these red circle dots really are the solution ICP-MS data points. And as you can see, the data sets acquired by the two independent techniques are nicely consistent, meaning that our protocol is well calibrated. So to summarize, our protocol for uranium lead dating of epidote employs the Tera-Wasserburg diagram, in which we plot uranium lead isotope ratios that are not corrected for initial lead and that are measured by LA-ICP-MS using an allanite as a reference material. So now I will show you the application, or two applications of the protocol and something more. And we will start in the eastern Swiss Alps, so in the Albula Pass area, which is part of the inverted Adriatic passive continental margin. So the Albula Pass area is shown here. It's the red arrow. And as I said, it is in eastern Switzerland. So the sampling locations V1, V2, and V3 are inside the albular granite, which is actually a post-Veriscan calcalkaline granodiorite. And it is the most common lithology of the air nappe in the study area. So the air nappe abuts the Ela nappe to the north, and the Ela nappe in the area is made of Triassic and Jurassic carbonate rocks. I will talk about carbonate rocks of the Ela nappe quite a lot during this part of the talk, and this is what I mean. So the air nappe and the Ela nappe in the Jurassic, so during Jurassic rifting, were respectively the distal and the proximal portions of the Adriatic Pacific continental margin. Tectonic inversion in the late Cretaceous led to the so-called Eo-alpine orogeny, and the Eo-alpine orogeny is subdivided into two phases. First, we have a compressional west-directed D1 phase, in which the Ela nappe was thrust on top of the air nappe. After that, we have an extensional D2 phase. So basically, we have top to the east. And after that, we have a number of deformation phases that we will not discuss today because they were not in the stability field of Epidote, and they were actually related to the north-directed main alpine orogeny. So Jurassic extension is embodied in the area by the Saluver breccia, which is this blue lithology here. And this is actually the infill of rift-related normal faults. And the Eo-alpine deformation is expressed by the tectonic relationships between the Ela nappe and the air nappe. And more in detail, in the specific area, the Ela nappe is both above and below the air nappe. And this is due to the deformation taking place in the D1 compressional phase. So the key points for us is that in the study area, we have clear evidence for Jurassic extension. And I can add that all hydrothermal features addressed so far are actually related to Jurassic syn rift fluid circulation. The Eo-alpine orogeny occurred entirely in the stability field of Epidote, and it never exceeded 350 degrees C. And notably, we actually don't know much about the Eo-alpine orogen, and in particular, we don't know anything about its elevation. This will become important when we talk about fluid pathways. So let's look at the samples. So these are the studied Epidote vein samples as they look like in the field. And they are subdivided into V1, V2, and V3, depending on the appearance of the host rock. So the only V1 Epidote vein that we have is hosted by the albular granite, but it also cuts a sandstone pocket that is enclosed by the albular granite. This is actually a local feature. V2 veins are hosted by cataclastic albular granite, and finally V3 veins are hosted by weakly deformed and weakly foliated albular granite. So here on the left, you have thin section scans in plane polarized light, and here in the middle, I am showing you the microstructures, also plane polarized light. So the V1 vein that we have is made of epidote and quartz, and it preserves growth morphologies ranging from blocky to elongate. V2 veins are also made of epidote and quartz. They also preserve growth morphologies ranging from blocky to elongate, and they cut the cataclastic portions of the albular granite. And finally, V3 veins are made of epidote and quartz, or epidote, chlorite, albite, and quartz, which are not labeled here because they're really small. And they also preserve growth morphologies ranging from blocky to elongate. So here in the middle, you have backscattered electron images by SEM. And so these are the studied Epidote samples. And the white circles are actually planned LA ICP-MS analysis for uranium lead dating. The different BSC contrasts, or the different shades of gray, if you wish, are related to chemical zoning in Epidote. And so, as I explained before, we try to sample all of them without mixing them so that we hopefully obtain the highest or the largest spread possible of the single analysis along the regression in the TerraWasserberg diagram. And here are the TerraWasserberg diagrams. So here on the right, you actually have insets zooming in because the data points plot very close to each other. So V1 Epidote unfortunately did not return an age. I can expand later if you want, but this is related to the fact that the data points plot basically against the y-axis, and so the lower intercept is not constrained at all. V2 Epidote returned a late Cretaceous age from analysis collected in both veins, so this is like a combined TerraWasserberg of V2 Epidote. And V3 Epidote returned a Paleocene age from analysis collected in 4 V3 Epidote samples. And you will hear the word unexpected quite a lot, because of course, if we are using a new tool, we may come across new information that we never gathered before. And so these ages are actually very unexpected, because I told you before that this area, so the air nap, is actually dominated by Jurassic rift-related fluid circulation. And here we actually have evidence for synorogenic Eoalpine fluid circulation. More in detail, the late Cretaceous V2 veining event is consistent with the compressional D1 phase of Eoalpine deformation, and the Paleocene V3 veining event is consistent with the subsequent extensional D2 phase of Eoalpine deformation. So if you look at the initial lat207 to lat206 ratios, V1 Epidote is within uncertainty of V3 Epidote, and V1 and V3 Epidote samples are strikingly different than V2, than the initial lat207 to lat206 ratio of V2 Epidote. If you remember, this initial lat207 to lat206 ratio is actually the isotope composition of lead that is transported by the epidote forming fluid. So we can use it to investigate fluid pathways. And we do so by combining lead isotope data with strontium isotope data. So just going back to the coffee pot, now we are investigating the lithologies with which the epidote forming fluids interacted. So the first hypothesis is that the epidote forming fluids interacted with the vein's host, albular granite, and with the rocks in the surroundings, so the carbonate rocks of the Ela nap. And we will demonstrate this using this plot. So in this plot, we actually combine data collected by 3 different techniques. I'm not going to go into the details. I can do it later if you want. But the important point is that all these ratios are at the time of fluid circulation, so at the time of veining, and I can expand later if you wish. I should also mention that in this plot, we actually plot the 4 V3 epidote samples. We plot them separately. And at a first glance, what you see is that V3 epidote and V1 epidote, first of all, they are quite similar, and they all plot between albular granite and carbonate rocks of the Ela nap. So confirming what we had hypothesized. So the fact that the V3 and V1 epidote forming fluids interacted with the carbonate rocks of the Ela nap before reaching the veining location in the albular granite. And because V1, so the isotope composition of V1 epidote can be explained by the same fluid pathway as V3 epidote, we allege that the undatable V1 epidote is also Paleocene in age. Now, late Cretaceous V2 epidote is quite similar to the others in terms of strontium isotope composition. So we may also infer that this indicates interaction of the V2 epidote forming fluid with the carbonate rocks of the Ela nap and the albular granite. However, its lead isotope composition is very, very different. And this may indicate that the fluid pathway of V2 epidote forming fluid, although it also interacted with carbonate rocks of the Ela nap and albular granite, actually followed a different fluid pathway. So what we understand here is that we have two different fluid pathways, a late Cretaceous one percolating through the carbonate rocks of the Elanap and reaching the albular granite from one direction. And then we have a Paleocene one also flowing through carbonate rocks of the Elanap and albular granite, but from a different direction. And I will make it clearer using a sketch in a few slides. So let's see if we can untangle these fluid pathways using or adding oxygen and hydrogen isotope data to the conversation. So here I am plotting, in this graph we are plotting the oxygen and hydrogen isotope compositions of the epidote forming fluids. And these are calculated from measurements in epidote grains at an estimated temperature of epidote crystallization. And we plot them in this graph against the isotopic composition of common water reservoirs such as seawater, meteoric water, metamorphic water, and sedimentary water. So oxygen is everywhere, whereas hydrogen is a bit scarcer, at least in rocks. This means that so oxygen in the epidote forming fluids is easily isotopically altered by fluid rock interaction. So imagine that we have a fluid source here, and this fluid interacts with granites and carbonates. So the isotopic composition of this fluid source will move in this direction, more or less, because of fluid rock interaction. So in terms of fluid sources for our epidote forming fluids, we have basically three options. We may have modified, and by modified, I mean modified by fluid rock interaction. So modified low elevation meteoric water. And the reason why we say low elevation is that the stable isotope composition of meteoric water evolves along this line from lower elevation to higher elevation. So in our case, we need low elevation meteoric water. It can also be modified seawater. And also, as you can see, the epidote forming fluids plot exactly inside the field of metamorphic fluids. So these are the three options. Now, this is the sketch that I was telling you about before. So we know from lead and strontium isotope data that every plausible fluid pathway has to go through the carbonate rocks of the Elanap before reaching the albular granite. And we have alleged that there are different directions that the fluid pathways can take. So low elevation meteoric water is a plausible fluid source if we assume that the Eoalpine orogen had low elevation. So it can be explained by the first scenario. The second scenario would be that in which we have a fluid source as modified seawater or formation connate water. And finally, metamorphic fluids is also possible as fluid source if we had prograde metamorphism occurring in the underlying units. So late Cretaceous fluid circulation was consistent with the compressional D1 phase of Eoalpine deformation, and so it may be explained by the third scenario if we had prograde metamorphism happening in the underlying Plata-Litsune-Malenko superunit. Paleocene fluid circulation was consistent with the extensional D2 phase of Eoalpine deformation, and it might be explained by either of the first two scenarios. Of course, these fluid sources are not mutually exclusive, and it's actually very likely that we have an interplay of the three different fluid sources. So I'm going to conclude this part of the talk, and as I said, we obtained very unexpected ages that beautifully, I would say, complement what we already knew about fluid circulation in an area that was already well characterized in terms of fluid circulation. And I also showed you how we can use epidote isotope geochemistry to learn about fluid pathways. And the point that I would like to stress is the fact that we have extracted all this information from one single mineral. So now we're going to leave the Alpes area and we're going to move to the central Swiss Alps. More specifically, we're going to the Grimsel Pass area. And this is part of the inverted European passive continental margin. So the red star indicates the location of the Grimsel Pass area. It is in the R Massif, and the R Massif is the inverted European passive continental margin. The studied epidote veins are hosted by post-Veriscan granitoids that were strongly deformed during the alpine orogeny. And alpine deformation is expressed by a network of shear zones. So alpine deformation can be subdivided into two phases in the area. So first we have a reverse faulting phase with green biotite stable in the shear zones. And this phase began about 22 million years ago and ended about 17 million years ago. And after that, we have a strike slip phase with chloride progressively replacing biotite in the shear zones. And this phase began about 14 million years ago. So alpine metamorphic conditions were in green schist facies conditions, and maximum temperatures were about 480 degrees C. And there is a lot of evidence for hydrothermal activity from the Miocene until today. So the studied epidote vein samples were collected in the GTS, which is an underground rock laboratory, and it's actually a tunnel. And it's quite amazing because on the walls of the tunnel, you can really see and trace all the structures that you can find in this granitoid. So here, this black feature is actually a mafic enclave, so a magmatic structure. You can also really appreciate the alpine shear zones, and here is an example. And you can really see and trace also the epidote veins. Now, the absolute age of the epidote veins is, at least for now, is unknown. And it is not possible to infer this absolute age of these epidote veins from cross-cutting relationships. However, before we talk about uranium-led geochronology of these epidote veins, I would like to discuss another important aspect. So if you remember, at the beginning of the talk, I mentioned that there are post-crystallization processes that can affect isotopic systems in geochronometers. And one of these is dissolution precipitation. So I would like to take a sort of geochronological break for a moment and discuss or show you the evidence that we have for dissolution precipitation of epidote. And then we will see what geochronology says. This is a sample that I would like to discuss. So this is the host rock, and it's actually called Central R granite, and you see that it's only weakly foliated. And here you have the epidote vein. And at a first glance, you see that the epidote vein has a funny internal layering, and we can subdivide the vein into 3 layers. So we have layer 1, which is dominated by epidote, and in which maybe you cannot see it, but you can also find some elongate epidote grains that suggest that this layer formed during veining. Then you have layer 2, in which the modal abundances of epidote are very variable, and you can see that the spatial distribution of epidote and quartz define a microfold. And when we move away from this epidote-rich band, we go towards lower modal abundances of epidote. And finally, we have layer 3, which is almost entirely made of quartz. And quartz in layers 2 and 3 is almost entirely dynamically recrystallized by subgray rotation recrystallization, as you can see from the shapes of epidote grains in this figure. So what we are particularly interested in is how the microstructure in layers 2 and 3 formed. And from now on, we will call epidote that precipitated directly from a fluid, so epidote in layer 1, we will call it epidote A. And epidote in layers 2 and 3, which has something to do with deformation, and we will see what, we will call it epidote B. So if you look closely here, you will notice that where epidote is most abundant, and we're talking about epidote B now, where it is most abundant, quartz has the smallest grain sizes. Where epidote is basically absent, quartz is much larger, and it reaches its maximum grain sizes. We also find anhedral epidote B grains measuring up to about 15 microns. We find them along quartz grain boundaries. So these grain boundaries formed during dynamic recrystallization of quartz. So they are the result of the response of quartz to deformation. If epidote precipitated here, then it means that epidote precipitated after the beginning of deformation. At the same time, I told you that epidote controls how large quartz can grow during dynamic recrystallization. So epidote must have precipitated here before the end of deformation. So in other words, this microstructure formed during deformation and epidote B crystallized during deformation. So these are mass fractions of selected trace elements in epidote. We have both epidote A and epidote B. What's important for us is that, as you can see, the patterns between epidote A and B are basically the same, so they overlap chemically, but epidote B is less variable than epidote A, and this suggests that epidote A and B have the same starting material. But if we look at lead and strontium isotope data measured in epidote A grains and epidote microseparates that mix epidote A and epidote B to different and unknown proportions, you see that epidote A is isotopically different than epidote microseparates. And we may infer that this indicates that epidote A is isotopically different than epidote B, and this is readily or more readily explained by invoking the addition of external lead and strontium to the system during deformation. So how do we put everything together? We have epidote B that crystallizes during deformation, but it has the same starting material as epidote A, and it is isotopically different than epidote A. So a possible scenario is this. First we have a veining phase in which epidote crystallizes into two bands. Next, deformation begins, and we have the grain size reduction of quartz by dynamic recrystallization by subrarotation recrystallization, while epidote is partially dissolved by an external fluid, which brings external strontium and lead into the system. The sliding of quartz grains relative to each other produce creep cavities in which epidote B can precipitate. And this dissolution precipitation process is repeated enough times to cause the chemical homogenization of epidote B. And the precipitation of epidote B along quartz grain boundaries is responsible for keeping quartz grain sizes small in a process that we call viscous granular flow. And finally, we have the present-day microstructure, which allows us to propose the occurrence of epidote dissolution precipitation. And the reason why this is important is that dissolution precipitation is a very important aspect of viscous granular flow. And viscous granular flow was the dominant deformation mechanism active in the alpine shear zones in the study area. And the other important aspect is that epidote is a hydrous mineral. And so when we dissolve epidote, we basically recycle previously stored fluids. So yes, and now we are all looking forward to finding out how old epidote A is, but I have to disappoint you, I guess, because epidote A actually returned a Miocene age, so a synorogenic age. And epidote A is Miocene, and also epidote from other epidote vein is also Miocene in age, and the combined Terra-Wasserberg gave an age of 14 plus minus 1.8 million years. So this is evidence for synorogenic fluid circulation. It's actually consistent with what we already knew about fluid circulation in the area. And the fact that we have green biotite, which is a typical alpine mineral, indicates that green biotite in equilibrium with the epidote, indicates that these are actually crystallization ages. So I promised that I would demonstrate the occurrence of pre-orogenic fluid circulation at the beginning of the talk, and actually I am not doing it, but these three variably deformed epidote veins are doing it, because the three are actually Permian in age, and the combined age is actually 276 plus minus 13 million years. This is actually really important because it's the first ever evidence, or the first hard data that we have for pre-orogenic fluid circulation in the study area. And these ages had never been detected by using other geochronometers. So you see that Epidote is doing something new. And we know that in the areas, in the Permian, the area was affected by transtension. And so our hypothesis is that the epidote forming fluids originated at the surface as meteoric water, and that they exploited thin rift falls to infiltrate the continental crust, interacting with thin rift sediments. And this is actually consistent with hydrogen isotope data of the Permian epidote forming fluid. I would like to stress once again that the fact that we have evidence for pre-orogenic fluid circulation implies that the preconditioning, so the weakening of the granitic continental crust in the European passive continental margin, started about 250 million years before the involvement of the continental crust in the alpine orogeny. So it's quite important. Something that I personally really like about one of the Permian samples is that if you look closely, you see that it has a funny microstructure that suggests epidote recrystallization during fluid mineral interaction. And in fact, if you measure hydrogen isotope ratios in this Permian sample, you see that the delta D is actually consistent with alpine epidote. And this allows me to make a kind of a crucial point, which is the importance of microstructural control. Because LAICPMS that we use for dating is an in situ technique, and this is more or less the size of the spot sizes that we use for dating. It's actually larger. For TCEA, which is the technique that we use for measuring hydrogen isotope data, we use about 4 milligrams epidote. So we basically homogenize at least this volume. So we homogenize everything. And again, as I said, it really highlights the importance of microstructural control when we want to do geochronology. But it also allows me to make another important point, which is the fact that old epidote ages are actually retained by epidote relics, even though these were affected by post-crystallization processes. So in the past few slides, I have actually given you the most important points of the talk, and I would like to take a moment to really digest everything, and then we will conclude the talk. So I have told you that we have evidence for pre-orogenic fluid circulation in the continental crust of the European passive continental margin. I have told you that epidote undergoes dissolution precipitation processes, and I have shown you that if we use the right technique, so if we sample the right volume, we are able to detect old epidote ages in recrystallized epidote grains. So the first point bears important implications for the hydration and the weakening of the continental crust in the alpine origin, because of a peculiarity of the R massif, which is the fact that in terms of structures, what we see here, we can follow here and we can follow there. So if we had fluid circulation in the Permian here, we probably also had it there, and we probably also had it there. And this means, as I said, that the granitic continental crust of the European passive continental margin was preconditioned for deformation, at least starting about 250 million years before the onset of the alpine orogeny. The second point, so as I said, epidote is a hydrous mineral. So if we dissolve it, we release water that was previously stored in epidote. And we often wonder if deformation localizes where fluids already are, or if it's actually deformation that drives fluids into specific locations in the rocks. And based on the data that I showed you, so that we have the recycling of previously stored fluids, but we also have the addition of an external fluid component when I showed you evidence for dissolution precipitation. It seems like we have a pretty complex interplay of recycled fluids and newly added fluids. And finally, finally, I have shown you that epidote can retain old epidote ages across orogenic cycles that involve deformation and fluid circulation. So in other words, I have shown you that epidote is a robust geochronometer that we can use to investigate fluid circulation in highly deformed granitoids in the continental crust in orogens. And as I said, we use the word unexpected quite a lot, I think. So the information that we extracted from epidote is unexpected, it's quite new, and it beautifully complements what we already knew about fluid circulation in inverted passive continental margins in the Alps. And of course, epidote is everywhere in Earth's crust. So I have talked about granitoids, but I suppose that many of you know that epidote is part of the mineral assemblage of seafloor alteration of basalts, for example. And so we are very much looking forward to expanding the applicability of the dating protocol to epidote from other lithologies. And with this, I would like to thank you for listening. I'm looking forward to your questions. Here you have some really nice pictures of the Grimsel Pass area and the Albula Pass area. If you want to chat more, if you have more comments, you're very welcome to send me an email here. And that's all from my side.
Thank you very much, Veronica. It was really nice talk, very exciting about the results you have presented and also what you can do with this method. We are really looking forward to see the other applications as well. So we invited everyone that are watching, if you want to send your questions, your comments, and I will start with Bruno. He already has some questions, as he has mentioned before.
Yeah, well, congratulations on your talk. It's really nice work. I've never done a lot of dating fluids before. Now that I'm working more with like mineral systems, I'm actually trying to do this. From the method perspective, what are the difficulties that you found during development?
You mean for the dating method?
Yeah.
Yeah, so mostly I am going to put up the presentation again. I will
In terms of
you.
like instrument and setting up, how difficult that was, in case people that are watching us are interested in doing similar things, what are the steps that they have to go through in general lines?
Yeah, so generally it's really important to have, as I said, microstructural control. So you really need to know what you are analyzing. So if there are any mineral inclusions, fluid inclusions, cracks, chemical zoning, you need to know your microstructure. And usually I find that BSC images are enough for my purposes, but otherwise also chemical maps are really, really useful. And then you can use those to plan your spots ahead, and then you go to the laser and basically you carry out the analysis where you want. So it's not a random measuring, let's say. In terms of instrument, so I've had only a couple of samples where uranium and lead were really, really low in terms of contents, and so it was basically impossible to measure. The main difficulty is not necessarily an instrumental difficulty, but rather the fact that if there isn't enough geochemical variability in your sample, you will never obtain a well-constrained regression, and therefore you will not obtain a useful age. And that's how you get these. I can give you an example. The undatable sample that I showed gave me a lower intercept of 20 plus minus 70 or something like that. So that's very much the issue. But in terms of measuring, so the actual work at the laser, it's actually quite trivial. It's not that difficult. You just need to have the standards, of course. The difficulty is more related to the uranium lead system in Epidote.
Cool. And what is the mass spectrometer that you use? It's just like a normal quadrupole, or do you actually use a multi-collector?
It's actually, yes, a normal quadrupole. I have a sketch just to show you. There we go. Can you see it, Noah? There we go.
Yeah, that's a quadrupole.
Yes.
Yep.
Yes, it's a pretty standard laser system, I would say.
And Veronica, coming back to what you were just explaining for the textural control, you have shown in the first example for the Albula granite that you have a zoned crystal, and then in the other example you have shown that even though they have your crystals have similar composition, they had a different isotopic composition. I was wondering, did you get different results for the first example? And do you think that the age could represent mixed age, or can you discard this issue?
You mean all the samples from the Albula area?
The one that you have shown, the compositional maps with the iron content. Yeah.
Yeah. Yes. Okay. This one, right?
Yes.
So the Terra-Wasserberg, so the analysis in the Terra-Wasserberg plot are actually from all different chemical domains. I think that the geochemical variability is rather related to different fluid pulses within the same veining event. So this is my current hypothesis. If it was mixed age, so if we had two different crystallization events, like for example, you have the crystallization of the vein, and then the system is closed, and then you reopen the system, we would have quite a lot of scatter in the regression. So I think that we can exclude the fact that we have partial resetting, because otherwise we wouldn't have such a beautiful regression. And I think that, so as I said, the spots were placed in all possible chemical domains, and they give you actually, maybe, I think I have the single Terra-Wasserberg diagram for this sample. No, I don't have it. This sample here, this is exactly the one of the Albula samples, and the age is 62.7 plus minus 3 with MSWD of 1.6, just to give you an idea. So from the statistical parameters, from the quality of the regression, and also from the fact that we don't have evidence for multiple veining events in this sample, I think that we can confidently conclude that this is only one age and that we don't have mixing of ages.
Thank you. Hesiani,
Yeah, can I just make a comment on this?
Yeah.
Yes.
A lot of the times we see chemical zoning in different minerals, and we already associate with different ages, and this might not be true because the chemical systems are not strictly linked with the isotopic systems. So you can just have diffusion of trace elements, but your isotopes is pretty much homogeneous throughout the whole grain, and then you're not expecting to find different ages.
Yes, and also you can also have the chemical evolution of the same fluid when it is actually crystallizing your epidote. So, and chemical zoning is epidote. I mean, if you don't have chemical zoning, you have a problem with your epidote. So that's a very common feature.
Hesiani?
Thank you for your great talk, Verona. I really enjoyed the talk. That it's really interesting, and I really like your presentation. And I love your coffee analogy. It's really
Ah,
nice to us to understand that it's really good. And I just have some questions about it. Do you have some idea how much, and try to quantify the water interaction? You know how much you see different sources, but the do you have some idea how we can estimate the amount of water in the interaction?
Um, I haven't done that. I honestly wouldn't know how to do that. I'm happy to take suggestions, of course, but to be honest, I don't know. I have no idea.
Okay, I was
And
just curious
Veronica,
about that.
yeah. And Veronica, you were mentioning that for locating the spots, you of course avoid like heterogeneities, and you mentioned the fluid inclusions. So I understood they are not abundant, but do you find any, and do you know their composition, or they are absent?
No, actually, there are many fluid inclusions. So the trick there is to make sure that, or at least to assess if it's primary fluid inclusions or secondary fluid inclusions and so forth. And also the fact is that um, compared to the volume of mineral that you sample, the volume of the fluid inclusions and the contribution of the fluid inclusions in terms of uranium and lead is probably not going to be that important. We do have them. There's many fluid inclusions in our samples, especially considering that this is also hydrothermal epidote, so it's quite common. I did so when we set up the protocol. I actually tried setting spots exactly on fluid inclusions to see what happens. So you also see the influence of the fluid inclusions, and the samples that I tested didn't really show an effect of the fluid inclusions when you sampled them.
I was curious also if maybe they would show from their composition difference that could support your results from the different type of fluids and events. Yeah, that's
Yeah.
nice.
Yeah, unfortunately, at the beginning of my PhD, I told my supervisor, "Oh, we could do some fluid inclusions," and he said, "Then you have to do two PhDs," and
Yeah.
so I couldn't do that, unfortunately.
Yeah,
But
sure. But it's
it would be
quite a
great.
lot of work or you have
Yeah,
done already. Yeah.
yeah. So, but it would be really amazing to do that. Actually, that would be a really nice complementary step.
Yeah.
When you talk, I fully agree with microstructural control. I'm all about having certain that you're dating certain types of microstructures in different minerals. But how do you deal with having to use a large spot size to date sometimes microstructures that are clearly mixing areas?
Yeah, so we use a 50 micron spot size. This is the we also tried 30 microns, and we didn't see matrix effects. The point is that I was quite lucky with my samples. That's the truth, to be honest. The sample that I showed at the end, where you have this where you have evidence for fluid mineral interaction. For example, I could not date the parts where you have this recrystallization. So I don't know how old the recrystallization is, for example. So um, personally, I like the idea that if you don't know what you are dating, maybe you shouldn't date it. Just to be sure that you don't present data that you have no idea about. Or you can do it, but then you don't tell anybody. But that's another story. And yeah, so that's how I deal with it. I live with the fact that at least at the moment there are some microstructures that we cannot date.
Yeah, well, that goes a little bit against the geochronology slogan. At least that is data first, ask later. So
Yeah,
people have the very typical way of dating everything they can, and then they try to understand it later, and sometimes it's just not possible.
yeah, I think it's fine, but then of course it's not. I mean, if you don't understand the data, you usually don't present them, I would say.
Yeah,
So yeah, of course you can try everything. But yeah, I agree. I would say it's just that
I have
I.
I have just one more question. Have you tried doing Epidote in mineralized systems, like any kind of mineralized veins or deposits in general, like in terms of ore deposits?
No, I haven't. I'm thinking, but no, I haven't. That's a next step.
Yeah, that would be very interesting.
Yeah.
Awesome.
I think it would.
Great work.
Yeah. Thank you.
Really nice. Thank you very much again for your talk, Veronica. We also have a comment from Ambrose Age. It's thanking for your talk. And yes, and you leave your contact. If anyone have more questions, they can contact you directly. Thank you very much again, and see you.
Thank you very
in
much for
another
the
time.
invitation. Yeah, thank you very much for inviting me. It's been a pleasure to present.
Thank you
Thank you,
very much for
everyone.
who have attended the talk and the hosts, and also to our collaborators that are also working in organizing the talks. So that's it. Have a
Yes.
nice afternoon, evening, morning, everyone.
Follow us, Petrochronics, on Instagram and Twitter, and here in the YouTube channel too.
YouTube. Yes. So also for our next PTT talk, the next month, it will be with Liza Batista, and we are going to start advertising soon. So see you next month, and thank you, everyone.
Thank you very much, Veronica. Bye bye.
Thank
Thank you,
you.
Veronica.
Bye-bye.
Bye bye, everyone.